All right. So last time we talked about linked lists. That was last week, where these are a structure defined by nodes and they're linked together. They're not fixed in memory. They can be kind of wherever we want them. As opposed to arrays, which is this rigid structure where all of these things are next to each other in memory and there's a fixed size. So we're going to continue our discussion of data structures, which is how do we store information in a way that makes sense? And so we're going to talk about two fundamental kinds of data structures today, stacks and queues. So we're continuing this unit. The reason why we're looking at things is like the question, there's different optimal structures to carry different kinds of things, right? To store different sorts of information, we need different structures. So for example, if I'm transporting my stemware, we're going to have this sort of carefully organized box where things aren't going to move around and run into each other and break. Alternatively, if I'm carrying around my computer, my iPad, my books, I'm not going to stick them all into a cardboard box and just carry that box around campus. I could, but is it efficient? No. So different ways of carrying things serves different purposes. If I'm moving a lot of books, then maybe I want to pack them all into boxes. But if I'm just carrying the ones I need for today, I'm going to have a different sort of structure to carry them. So these are the ones we're going to talk about. First, we're going to talk about stacks. A stack is a kind of structure where, as its name suggests, computer scientists tend to be a little bit terrible at naming things. And so if we see something, we name it like it is. And so if you think of like if I have a stack of dishes, if I'm unloading from the dishwasher, I'll put the first one on, and then the second one on top of that, and then the third, and so on. And so I have a stack of things. That's this kind of data structure where I add things to a stack, one on top of another, and then I can take things off of the stack. If you think about the dishwasher example, if for some reason you want a plate in the middle of the stack, it's like super tedious to get it if you've got this whole big heavy stack of dishes, because then you have to like lift it up, grab it, and hope that nothing falls and breaks as you do that, right? So there's some limitations to, we don't want to go in the middle of the stack at all. We just want to interact with the top of the stack. And that's this kind of data structure. This data structure allows only two main operations. So that means we can only add to the top of the stack, and we call that operation push. And we can only remove from the top of the stack, which we call pop. So here, if we start with an empty stack, we push the number 1 to the bottom of the stack, or to the top of the stack and the bottom because it's empty. And then we can push 2 onto the stack, can push 3 onto the stack. And then when we want to remove something, we pop. And so when we pop, we take it off of the stack and we hand it off to whoever asked for it. So for example, if I want the top plate in my stack of dinner plates, then the person who has been stacking them takes it, turns, hands it to me, and then I walk away with that plate. So the value that pops gets returned. Okay, that's, oh, maybe it's not actually quite incorrect. Okay, so my example is, I've got Pringles cans here. The Pringles can, if I open it, I can only take out the top chip. I cannot, it takes so much work to like carve a hole in the side of the Pringles can and then grab a chip. it's going to lead to things getting broken. I can't do that just like with the Pringles can that I have. The only way to add or remove something from this can is to add or remove from the top. And this is what we call a first in, last out structure. You can flip those around. So the first thing you put in is going to be the last thing you take out. The first dinner plate you take out from the dishwasher is going to be the last one you end up eating from once you've used all the other plates. Alternatively, the last plate you put on the pile is the first one that's going to get used. Right? So the last Pringles chip that got put in the can is the first one that you're going to eat. There's another operation called peak that a stack has, where peak is basically, I've got this information and I can say, here's the thing I have at the top of the stack, but nothing changes. So I don't remove it at all. I'm just saying, this is what it is, but my stack's not going to change. So this seems super simple. It kind of is, but it's used for some really important things. One of which is what we've been seeing this whole time. So when you're writing your program and then something goes wrong and it gives you this error message, it's actually giving you a stack where it says, here's where something went wrong, and then here's who called me and who called me and who called me. And that's a stack. So let's maybe think of an example. Right, let's think of code that I have that's not going to work. All right. So this is lab 6 code that I have not implemented. And it says exception in thread main, not yet implemented. But then there's other information of where did this error come from? And so the way that the compiler works, so behind the scenes, whenever we save something, Eclipse compiles it, which means it takes it from our human readable code that we've written and translates it into something that the machine can actually run. That's what a compiler does. And when something goes wrong at some point, then it has to report, here's where the error happened. All right, so let's, all right. All right, so this is my error message. And so what happens when we run a program is there's the stack that maintains the compilation records. And so essentially, when we go and call main, we're like, okay, computer, run main. And then main goes through and it is trying to call other things. So in this example, I think it's the old linked list code where it tries to call union and union throws an error. And so what happens when we run a program, things get added to the stack and removed from the stack as they finish. So if in my main, I call function 1, function 2, which calls function 3, and then I call function 4. First, when I run this, it's going to call main. So main gets pushed to the stack. Then in main, I call function 1. And so function 1 gets pushed to the stack. Function 1 goes and does its thing. And then it's done. Once something is done, we pop it from the stack. So that's done. And then it's time for function 2. In the process of function 2, we call function 3. And then when function 3 is done, we pop it from the stack. And then when function 2 is done, we pop that from the stack. And then we call function 4. When function 4 is done, we pop it from the stack. And then main is done. We've done all the things that main needed to do. So we pop that from the stack. And so sometimes if you're looking at like reports of if like your program ran, but it didn't do anything, you'll say like stack trace 0 or something, where like we have an empty stack, so it finished. I did all the things I was supposed to do. Other times, if it comes back with an error code of 1, then hey, there's still something on the stack. So something over here didn't finish running, ran into an error. So that's what we call activation records. And so that's how the compiler works behind the scenes. There's also something called the OSI stack. So if you ever take a networking class, this is basically how the internet works. And so there's different layers of the stack where you go through each one, and each one has an increasing level of, or a decreasing level of abstraction. So you go down to like the physical layer where it's the actual like wires that connect one place to another. So yeah, so that's also a stack where we go down each layer, and then when a signal is received at the other position, it goes up from the physical all the way up to where like I can go check my email, the application. All right, so yeah, so this is another example of the call stack where if we call function 1, 1 calls 2, 2 calls 3, and then as they finish, 3 finishes, so it gets popped, 2 finishes, so it gets popped, then 1 finishes, and we're left with an empty stack. All right, so with your neighbors, I have markers at the front. I also have objects that you can use as a stack. So come up and choose your favorite. And I would like you to write on the board what are examples of stacks in everyday life. You can draw it if you want. And then I will come around and I would like you to demonstrate push, pop, and peek for me. Sounds good? All right, go for it. All right. Nope, I would like to go back to my pen. Okay, so thank you for that. So I just want to clarify one of the things where if I have added something to a stack, and then when I go to pop it, then I need to I need to remove it from the stack, and I need to return the thing that got popped. So let's say I'm going to push the letters of the word hello. So if I push that first, there's an H, then there's an E, then there's an L, another L, and then O. What's at the top of my stack? Oh, right. So if this stack is called S, then S.peek gives us the letter O. S dot pop will remove the letter O, but it should also return O. So it will also return the letter O to me. So if I call S dot pop again, then if I call S dot pop from bottom to top, what's in my stack? What's at the bottom? H. What's next? E. What's next? What's next? So if I've got this stack, it's hell, and then I call pop again, I'm gonna have H, E, L. Anything else? No, because I've just popped something from my stack. And the important thing is that I walk away with what was just popped. So it will return L as well. This continues for our next data structure. So the group over here had an example of cars in a drive-through, which is not a stack, because if you think about it, it's not a first in, last out structure. So the first person who arrives, it's like if we go to McDonald's and we're waiting in line, and then the person who just joined gets their food first. That's not how a drive-through works. How a drive-through works instead is the first car arrives, orders, then gets their food and drives away. This is a queue. And this one is really intuitive. It's a line of elements. So if you think of like the queue at a grocery store, if you're at Safeway, you've got your items, you get in line, and then when the cashier is ready, then you will exit, quote unquote, exit the line, and then your items get checked out, and then you go. A queue, both of these are linear structures, meaning that they function in a straight line. So typically for queues, we draw it horizontal. For stacks, we typically draw it vertically, but it's still just a line. And so for a queue, we've got two operations. So instead of just the top of the queue or the top of the stack, we've got the front and back of the queue, right? So for a drive-through, there's the car who enters and orders, then the car who gets their food and leaves. So there's the back of the line and the front of the line. The operation for joining the line, so entering at the back of the line, we call enqueue. This is ENQUEUE. Lots of U's and E's, I'm aware. And then the operation for leaving the line is called dequeue. So enqueue, you're joining, dequeue, you're leaving. And so if we have these labeled, so like the front of the queue, the back of the queue, enqueue is when we add to the back of the queue. Dequeue is when we remove from the front of the queue. Queues are also used for really important things. So your operating system on your computer schedules things. So this is like all the processes of I need to download the web page from the internet, to I need to keep the clock running, to I need to make sure that like if you press a key, then it shows up on the computer. All those things in your operating system are scheduled, and this is a queue. Happens to be a priority queue where certain things that need to happen like regularly, like the clock needs to be updated, that happens more frequently. And then less important things are like, you can wait until later. That's a special case of a queue. So, okay. I think I may have forgotten to update this slide deck again. Let's think of I'm so let's say if I'm typing, and then I press undo, is that going to be a queue or a stack? Stack. Why?
Because you stack takes out the end and when you type in undo it, it does what you just.
Right. Right. So it's not like if all right, let's go back to hold on. Here for built-in display. There we go. So yeah, so if I type like all that stuff, and then I hit Command Z, that word isn't going to be removed first. The one I most recently typed, well, okay, that wasn't helpful. But the word I most recently typed is gonna disappear. And it's gonna disappear like most recent. And so also if you are in so if you're in your web browser and you go from link 1 to link 2 to link 3, the back button is going to take you to the most recent thing. So that is actually a stack. But thinking of like if you're working in a grocery store and you've got the like you go and get milk, they load the milk in from the back and then you take the milk from the front. That's a queue. The other example is how many of you have used like a super old printer? And do you know how like if you send something to the printer and then you're like, oh wait, no, I need to change that. And you make a small change, you send that to the printer, and you're like, it's not printing. Let me send it 5 more times. A printer works on a queue. And so the very first thing you sent to the printer is going to get printed first. And then the next thing, and then the next thing, until the most recent thing that you sent is going to finally be printed last. All right, so we're going to do the same thing of what are other examples of a queue that you can think of. And then I'll walk around and I would like you to demonstrate NQ and DQ for me. The cups are kind of, there's stacks of cups, but you can figure it out. Of maybe put them in a line or something. All right, go for it. All right, thank you. Let's see. Trying to think. Nope, the thought's gone. Anyway, right. So the same thing, the same sort of idea holds. What we're looking at here for both cases is a linear structure where we can draw something as like in a line. And the only thing that matters in this case is which ends do you have open? So for a stack, there's like a bottom to the stack. And so we can't reach through, drill a hole from the bottom. We can only add things to the top and remove things from the top. So examples for this is like a vending machine. An example for a queue is like someone had an analogy of like when you're joining a multiplayer online game, right? Where when you log in, you get added to the queue. And then the first person, like if you have a better internet connection and you were able to log on sooner, you get into the first game where someone who waited a little bit longer has to wait to join a game. And so NQ is when you get added to this list. And then DQ is when you're actually get to go and start the game. So now we need to be able to implement this. So it's nice to have these ideas in theory. We know what sort of operations we want stacks and queues to have, but we need to be able to implement it in code. And I want to be able to do that without prescribing exactly how this is going to work. So remember, we were talking about these abstract data structures where we have some functions, some methods, and then we have some way of representing this data. So I would like to know if this is our core functionality for these kinds of structures, how am I actually going to store the information? So let's say I have a stack of coins. How am I going to build my class? Where does that data actually get stored? If I have a queue of gamers, like let's say gamer is one of my objects, how am I going to store that information in a Java class? Okay, think about it for a second. How am I going to actually store this information? And then turn to your neighbors and talk about it. Like what sort of structures am I going to use? How am I going to actually maintain this data? Go for it. So we've got two kind of different possibilities. So we need to be able to store this linear data in some sort of linear structure that we've talked about. Two such linear structures are an array, which has fixed size, but I mean, even if we run out of room, we can always reallocate, so that's not a big deal. And we have a linked list. Right? Both linear structures, both good options to store this information. So are they gonna be different, the way that we approach actual code for this? Would it be different to work with a linked list versus an array in terms of the actual code that we type? I think the answer is probably yes, right? If we use an array, we're using different syntax than we would for a linked list. So I don't know. I don't want to necessarily prescribe like this is the way that you implement a stack. This is a way that you implement a stack, like using an array, using a linked list. So this is where it's a good idea to use interfaces to say, I know what sort of high-level operations I want my stack to have. I know that I want my queue to be able to enqueue and dequeue, but I don't want to prescribe, here's exactly how you're going to store all this information. Like I could store it in an array, I could store it in a linked list, but I could also, I don't know, make a new field for everything that I have. Like I could choose to do it some wild other way. And I don't necessarily want to like prescribe, here's how you have to do it. So I'll make an interface, which is this is how I want it to work, and you figure out how to do it. So let's open up Eclipse and create these interfaces. All right. What are my packages called? I've got U5 data structures. So let's put it in there. So actually, nope, I'm not making a new class. I'm making a new interface. So I am going to parameterize this with the angle brackets because my stack will contain some kind of thing. So either it's Pez candy or it's napkins or it's a plate, right? It's going to contain one kind of thing. And in my interface, this is just a method contract. There's no fields. And so my methods are implicitly public and abstract. And so for a stack, what methods do I want? Yeah. Push, pop, and peek. Those are my stack methods. Push, pop, peek. All right. What's the return type for push?
Oh, no, sorry, void.
Void, why?
So, push is when you bring something in.
Mm-hmm.
You get something.
Correct. So when I push something to a stack, I don't need anything in return. I just need something to happen. So void push. Do we have any parameters? Yes. What is it?
Object you're pushing.
Object you're pushing onto the stack. Can someone else tell me, like, what do I type? T? So remember, parameters have, like, I need the type name and then the variable name. So I just need a variable name. I can call it X or whatever. So T is the type of thing that I am pushing onto the stack. X is whatever I'm going to call it. I can call it X, I can call it data, something. Doesn't matter. All right, so for pop, what does my return type need to be? Can this be void? No. How come? Someone who hasn't answered yet. Has to return whatever it pops. So what should the return type be? T. Do you need to take any parameters? Nope, because I'm not adding anything. I'm just removing something. And then for peek, what should my return type be?
Push the T's one.
Also T. Do we need any parameters? No, because we're not giving it any information. We just want to receive information. Excellent. All right. Let's make another interface for a queue. And so for a queue, what are my two important methods? DQ and NQ, onQ, DQ. Pronunciation varies. For DQ, what is my return type? Again, like not a trick question. What's my return type for DQ? T. Again, because I'm removing something and returning it. Do I need any parameters? No. I don't need to give the Q anything to remove it. What about NQ? What's my return type?
Cool.
Void, because I need you to take something. Do I need any parameters? Yes, what are my parameters? Yeah, so T and whatever. Great. That's my interface. This is my method contract to say anything that is a stack has to implement these methods. All right. So I'm going to Okay. So originally I was like, I'm gonna do this with linked list code that I wrote. I may just use Java's implementation. So for a stack, if I'm using a linked list, and if this is the head of my list, let's say this is 1, 2, and 3. I want you to figure out if this is the contents of my linked list, how do you think that should correspond to what my stack looks like? So talk with your neighbors for a second. What's at the bottom of the stack? What's at the top? What order do we go in?
Can you access this one? Anyone have that?
I think
You can have that.
you do like virtual, but like the like.
It's so.
But I think.
All right. So we've got two options here, right? So either the head is at the top of the stack or the head is at the bottom of the stack, because there's like two ways we can orient this list. Which one makes more sense? Do we vote for option, hold up a finger, 1 or option 2? See a vote for. Okay, so I think we're kind of evenly split. I think there's slightly more votes for option 1. I think intuitively for me, option 1 would be what I go with. Because that. Oh my gosh, where did we go? There we are. So let's say I have an empty list and I want to add 1 to my stack. 1 is now at the head of my list. And let's say I want to add, so that's another option. Let's say I want to add 2. So either we now we draw an arrow that way. And so now we're over here. Or we add 2 to the head, to the front of the list. And then now we've got 2, or now we've got 1 down there, and 2 is at the top of the stack. Intuitively, for me, I think option 1 is the way to go. The reason why, let's say I have a stack of 50 million things. To add something to add my 50 million and 1th thing, I need to start at the bottom of my stack, go through all of them, take all of the links, the 50 millionth thing, and add that new thing right after it. So we would start here at the bottom, go all the way up to the top, and then we can add our new thing. That takes work. It takes time. As opposed to if I add my new thing to the head of the list, I don't need to traverse any links to get there. I just need to, like, okay, this is my new thing. It points to the old head. Now head points to me. That's way more efficient than going through every single thing in my list to get to the end. I think you could argue equivalency. No, no, it's not equivalent. If we use singly linked lists, so where the links can only go one way, if I'm at like 5 up here, maybe I have a tail pointer at the top of my list. Even if then I can just like access that immediately. But when I do that, I need to update tail and I can't go backwards. So I need to start at the beginning, work my way up of, oh, here's 4. 4 is my new tail. Do you see how that's inefficient? Where if I have to start at the beginning all the time and work my way up, we don't want to do that. So for my stack, when I demonstrate it with a linked list, I'm going to have the head of the list be the top of the stack. And whenever I add something to my stack, whenever I push something to my stack, I add it to the front of the list. Okay, I'm choosing not to use that. I will instead use Java's linked list. Okay, so I'm going to create a new class. I will call it LLStackT, and I would like to add my interface, the one that I created, and finish. All right, so my abstract methods got inherited. And so currently they don't do anything. But first I need to decide what's my actual data structure. So I'm going to use a linked list. So I'll use linked list LL. Linked list is a raw type. So I should probably give it T. Linked list. Nope. Okay. I'm currently having an issue where it's referring to the linked list class that I wrote previously. I don't want to use that one. I want to use Java's version. So I'm going to rename that one. I'll call it like linked list 1 or something. And so I would like to use linked list, in particular, Java's linked list. Java util linked list. And so this is someone at Java has defined basically the class for the computer list that you did on Thursday. They've written up that class and it has all of these functions that you would like it to have. So let's open up and see what that looks like. And so it has all the sort of methods that you wanted to have, but it is a linked list. And so it relies on nodes. So that's how it is structured in its code. Okay, so we need our stack. And so we've got the linked list. That's going to be the structure that we build on. And so to push our item, so first maybe we need a constructor. And so if we want to create an empty stack, then we will just instantiate our linked list and say, okay, here's my empty list. All right, so to push something to my linked list, LL is the variable that holds this list. So I've got some options to add at some index, add first or add last. Add is the same as add last. If I hit enter and go with that, is that what I've decided is good? Thumbs up, thumbs down? The answer is thumbs down. Why? Yeah,
So that would be so.
right. Yeah, the head of my list is the top of my stack. That is an assumption that I, the programmer, have made. I have decided the head of my list is the top of my stack. And so I do not want to choose a method that adds it to the end of the list. So I'll do add first instead. So I can just add that over there. For pop, so LL is where all of my items are. And so I've got options. So element retrieves but does not remove the head first element of this list. Get returns the element at the specified index. Get first returns the first element. Get last returns the last element. And then they've got peek, first, and last also implemented. Talk with your neighbor. Which method should I choose? All right. Am I getting it at any particular index in the middle? No, because it's a stack. I only work with the top of the stack. So is it get last? No, it's get first because the head of my list is the top of my stack. The first thing in the list is the head of the list. Am I done? No, why not? Right, I have to like actually remove it. Okay, so this is actually peek. We've done peek. So I'm gonna copy this and then paste it over here. So either we could like save that to a variable and then if we remove first, but okay, let me read this to you. Removes and returns the first element from this list. So the way that they have structured their linked list class is if I call remove, it removes it and then it hands it back to you. So I can just call the remove method. So I just call remove first. And then that gives me, because I read the documentation, that gives me the item and then I can return it. Great, that's my stack. If I want, I can add a size method. Size must return something of type int. How could I know the size of my stack? First of all, how is the size of my stack defined? Yeah, so the number of things in it. So if I'm using a linked list, the number of nodes. So a linked list knows, like, I think a linked list has something get size. Linked list dot size. So it's got a method to do that, and so we can just return the size of my list. So now that we know how linked lists work and we know how arrays work, we're kind of wrapping that around to only allow for operations that we define. So only push, pop, and peek. Those are the only operations we care about for this structure. But it's based on the underlying structures of a linked list or an array. All right. Would like to get to queues, so I think we will skip that for now. I would like you to think through this for a second. So if you look at, so I'll have you work on the board. So if we draw a linked list like this, where we've got boxes and arrows, where if this is the head, so I have a hint here, doubly linked, but try and draw something on the board of how do we make a queue into a linked list? How do we base a queue off of this kind of data structure? So my argument is that you need to have arrows going two ways. Am I correct or am I wrong? So draw these boxes and arrows on the board and decide where's the front of your list, where's the back of your list, and how do you make sure that these operations work as efficiently as possible? All right, go for it. So this involves when we have links going both ways. So let's say that this is the front. We'll call this the head. And then we can have the tail, which is the back of the line. So previously you defined a linked list as this is the head of the list. You can have two fields to say this is the head of the list and the tail of the list, the front and the back. If we do that, then when we go to add another thing to the back of the list, all we need to do is point that arrow that way and then update these pointers. So the back or the tail, whatever we're calling it, now that's there. We did not need to iterate through all of the list. We didn't need to start at the head, go all the way down. So we've removed that. We've made it more efficient. And removing from the front is, like you mentioned, not that big of a deal. But I will caution you that if we have something here and we want to remove it, then head's not there, the front's not there, this is the front. Is there anything different about this situation than when we removed something from a list before? The answer is yes, but why? Okay, so this is the front of the list. And now I'm in a new world where I can have nodes of, for a node, I can get the next thing and I can also get the previous thing, right? Right. So the problem with this, if this is the front of my list and so this is no longer the head, I need to make sure to actually sever this link to say that my new thing in the front does not point back to the old front. So in code, this would say something like the head dot set previous to null to say, I'm not pointing back there anymore. I don't know them. Okay. So we don't quite have time to do that. We'll maybe get to that next time. I want to spend the last few minutes talking about some variations. So when I brought the boxes for the linked list, I remember one of you had like a linked list kind of like this. Right? This is what we call a circular queue, where if things need to happen repeatedly, then we maybe have a structure like this, where there is the front and there is a rear of the queue. Maybe it's all filled up, and so we'll go around the circle like that of first this happens, and then we need to enqueue it to happen again later. So like if we're updating the clock, update the clock, and then we can do stuff, but we need to update the clock again. And so it's like we tie it all together. And then there's this notion of priority, where some things need to be dequeued first. And an example of priority is, let's say you go to the hospital, and if you just have like a small thing on your arm, then that's less severe than someone whose knee is injured versus someone who had a head injury, right? Some things are more severe. So like if you go to the hospital and you complain of like chest pain, you're going to be seen sooner than someone who like just needs stitches, right? So there's this notion of priority. So if we enqueue something with priority, so if we have like A with priority 1, C with priority 3, and then we enqueue B with priority Q, or B with priority 2, B skips over C, and now is before that. And then when we dequeue, we'll dequeue the highest priority thing at a time. All right. In terms of where this class goes, the next class after this, 374, we'll talk about priority queues in more detail of like, how do we implement them? How do we actually make this happen? This may be a question I ask on the final exam of how would you implement a priority queue? Not expecting you to do it, but if we implement something with a node with a linked list, how do we add priority into that? What changes do we make? So those are the things that I want you to think about as we get into these higher level abstract structures. We need to think about how would I implement that in code as an object. And so if we've got these basic things, then it's just iteration to add some new element to that. All right, next time we will work on lab 7. Thank you for coming. I will see you on Thursday.